vision can help us with that. Okay, that is good. Just need to share on Teams again. Okay. So I'm going to start off talking in the context of disasters. I had a slide too, but if I go to that, it seems like it's working now. So here are some of the things that we do in our lab. We've been working a lot on how to make digital twins of bridges, and computer vision can be very useful for this. In general, for to make a digital twin, you need to acquire some data from a structure. So what is a digital twin? It's a virtual replica of a structure that can be periodically updated and can be used towards some outcome. So you need to decide what that outcome is. Like we discussed, before you collect your data for photogrammetry, even if you're making a digital twin, you need to have some goal in mind. And then you can have a cyber physical interface, which is what connects the physical asset to your virtual model. And to do that, there are different data acquisition platforms that you can use. There are different sensors that you can use. In this course, we're mainly looking at images. And then once you collect that data, then you can process it and try to produce models. We also work on multispectral data to try to fight hidden damage. I've shown you some of this. We also work on fundamental AI computer vision advances that are more broadly applicable beyond just civil infrastructure, but also have some applicability in civil infrastructure. And then we also work on different robotic tasks that can be useful for repair after damage assessment. Now, in the context of disasters, I told you about this as one example of a situation where you need quick inspections at scale, especially if you have a large disaster hitting a densely populated region. You will have a lot of damage. So in the US and in many countries, the way this works is after a disaster hits, then quickly you want to localize where that damage is and try to get your best estimate of the extent of that damage. And this is typically done in the hours and days after the disaster. And in the US, this is called a preliminary damage assessment. It's done by local government and volunteers. One of the things that they're looking for, apart from where to assign recipe upwards, is the eligibility for federal aid, because in the US there are some thresholds. So if it's a large disaster, then you will also get some money from the federal government to help with the recovery. And then there are individual assessments which are done by FEMA, and this determines things like insurance eligibility, the amount of aid that you might get if it is a federal disaster, and whether or not it's safe for you to well, the safety is also assessed here and is assessed there as well. So all of these assessments, as you can see, can take a lot of time. And if you are in limbo, then you can't really, it slows down the recovery of the economy, of the society, and nobody wants this. Private bill. Yeah. So there's a flood insurance policy, for example, which is national level, which everybody pays into. And then there's a determination of whether or not you can get this aid. Yeah, so that there's that, and then also of course individual homeowners will have insurance, but may not be insured, and so if you do have your own home insurance, then that will take first preference. But then still there are many homes that need this, and it also can be used for determining the safety of the structure, and that if they say that it's unsafe, then you're not allowed to go back into the structure. Yes. Okay. Now the problem with the current ways things are done is that it's a door-to-door inspection, so it takes a lot of time. There are safety risks similar to the ones I described, after the earthquake in Mexico City, because the structures themselves may be unsafe. And to give you an example, in Houston, after the big hurricane that hit in 2017, Hurricane Harvey, nearly 5 months after Hurricane Harvey, hundreds of thousands of applicants' homes had not yet been inspected, because the scale of that disaster was so large that there's just not enough resources to go and inspect all of these homes. So if you can use some data available to reduce the number of inspections you need to do, then that can go a long way in facilitating faster recovery of affected areas. So, we're interested in how can we use automation, how can we use latest advances in technology to help address some of these challenges. And inherently, it's a multi-scale problem, because you want to be assessing things at a city level, but you also want to get the details of individual structures. And it's not that the same methods will be suitable for all of these. So you have to have different approaches tailored to these different scales. But in terms of the computer vision aspect, there's a lot of things that can be reused across these approaches. So let's look at two areas of advances in post-disaster assessments, using more data sources and using better post-processing methods. So for data sources, commonly used sources of data are satellite imagery, because of course this gives you low latency, high coverage data, and that's great if you're trying to do city level assessments. There are some challenges. For example, the resolution is of course compromised, and also after hurricanes you can have cloud cover, and that limits how much you can see. But even after other disasters, you could have cloud cover, and then with optical imagery, there's a limit on how much you can see. There's also UAV imagery, which is very convenient. You can get much closer to individual structures, and you can get much better resolution. But if you want to scale this to an entire city, then again it becomes challenging. You guys experienced flying a UAV, and it has a very limited battery life. And even if you were to do just this building, it would take, several minutes. To do a whole city, then it can take a lot longer. So it's time consuming, and you have limited coverage. You also have all of the regulations that you need to deal with when you're flying in lower airspace. And then, of course, you can take ground level imagery, which is very popular. Which is a very popular choice, because you don't need to worry about regulations. There's a lot you can see from the ground level. For taller structures, it may be harder to get this because the top of the structure is further away. Of course, you can use zoom cameras. One downside is you cannot see the tops of the structures with just ground level imagery. And so that poses some accessibility issues. But also, since you're trying to get close to the structure, that can also pose a safety risk. As far as post-processing methods go, with satellite imagery, one common method that people adopt is change detection, where you have a reference and you have another image that's taken after the disaster, and then you can use different sorts of approaches, including deep learning approaches, for change detection. Now, sometimes you may not have access to satellite imagery from that area. You can task a satellite to get data, but if the area that was affected was not covered prior to the disaster recently, then that may not work. And many of the methods that were proposed until 2022, they had low F1 scores, which is a metric that can be used for different things, but indicating lower performance. We've looked at semantic segmentation. Here, this can be useful both for large areas, but also for individual structures if you want to get details. But here some issues are, it takes a lot of time to label, right? Because there's a lot of detail there. You want to get that working, it takes a lot of time. And then again, there's limited generalizability, so you want to keep growing your data set. And then there's a direct classification approach. So here was a paper where they combined multiple views, had a satellite view, and then they also had ground level views. They combined all of that and they tried the model. But still the accuracy was low. So here is a building level accuracy. They're doing a classification of the whole building, and they're comparing it to what a human inspector assigned when the human inspector was at that building. And you can see that the accuracy just with the satellite is 55%, the multi-view is 65%. And here they were using a CNN architecture. Now, if a human is looking at satellite images, then they will have an 70%. They've been trained, according to this paper from Luz et al. And what that means is that with this sort of satellite imagery, that is what a human can infer about the damage state. Okay, so this is not a human looking at the building, it's a human looking at a satellite. Now, like I said, in autonomous driving, there has been a lot of advancement in AI perception, which, and by that I mean AI computer vision, that can perceive very, in real time what the car is seeing around it. So much so that many of these companies are able to have self-driving systems that can drive tens of thousands of miles without a human intervention. Obviously, that means that their perception systems are very robust in those environments. And the question then arises, why can't we have such robust systems for the inspection systems and for the post-disaster assessment systems? The problem is that this is a very well-funded industry, and there's a huge market potential here. And because of that, there's huge motivation to perfectly map out all areas and enable this sort of application. But for inspections, that that motivation, that financial motivation, is not the same, because in people's minds, the infrastructure assets are there, they're surviving predominantly. There are disasters that take place, and there are unforeseen that take place, but it still remains seen what level of resources might eventually go behind maintaining those infrastructure assets, because disasters are a relatively rare occurrence for a single region, and so it comes into the minds of peoples and then goes away. Routine assessments are a persistent challenge, but even then, not as persistent as sitting in a traffic jam or having to drive and losing 2 hours of your time every day. So that's the main difference, I think. That being said, there are things that we can do to, even at a lower budget, do our build our models so that they can have the best performance possible. So there's a lot of room for research because of that. Well, that's my opinion, anyways. So how can we improve assessment accuracy, the limited data that we have from the assets that we can survey? There are 3 research topics that that I'll touch upon, and then we'll look at some other topics as well. First one is semi-supervision with unlabeled data, and then I have unsupervised domain adaptation with CGI data, and then I have generative for data augmentation. The first one is specifically for post-disaster assessments. After a disaster, like I said, you have large areas that could be affected. Here we looked at trying to use a new type of data. So it's different from satellite data, and it's called ultra-high resolution aerial imagery. You have an aircraft that's flying at about 2 kilometers, and they have an ultra-high resolution camera. So this gets 4 to 5 times satellite resolution effectively, and it gets multiple pictures at the same time. So you also can get oblique views, not just the nadir views. And there's this company called Vexel that goes out and collects this UHR imagery within 3 days after a disaster. So we worked with them, and they shared some of their data. And we correlated that data with on-the-field observations after hurricanes in the last 7 years. And to do that, we used the Google Maps API to identify building footprints, and then we had the data for each of those buildings. And we were able to assign individual damage states to buildings. And then we used a transformer model called the Vision Transformer to simply classify the images of the buildings into the damage state. So it's similar to that satellite example I showed you, except we're using better data because we have this ultra-high resolution aerial imagery, and we're using potentially a better model, because it's a transformer and not a CNN. And then one thing we realized is that we have ground truth for the buildings that were assessed by the researchers. So we have about 1,000 or so images for which we have the ground truth. But we have tens of thousands of images that don't have any ground truth. And there has been a lot of advances in self-supervised learning where models can learn without specific ground truth. And so we investigated applying some of these self-supervised learning models to this problem of post-disaster assessments. So let's look at the classes as an example. TEMA defines 5 damage states for post-hurricane assessments, and they have specifics on when a building would be classified into a certain damage state. Now, based on that, reconnaissance researchers that are going out and looking to study how buildings perform after a disaster, they collect images and do these assessments. So we have the ground truth in that categorization. Here you can see a comparison of a satellite image and a UHRA image, the same buildings after the same disaster. And you can see, of course, the clear improvement in the resolution. And you can see the gradation of damage classes. One thing that we wanted to study was the comparison of a fully supervised approach versus adding semi-supervision with a lot of unlabeled data. So in this case 1, we use all of the labeled data. So labeled data means that each of those images has that ground truth by the people who were at the field. And then we also use 25% of the data only as case 2. And then we use it to train a vision transformer in a supervised way. It's trained for 250 epochs. And you can see the accuracy here. So the accuracy in this case is the number of buildings that are correctly predicted. And of course, with more training data, as you would expect, the performance of this model is better. Now, just comparing this to the performance of the satellite satellite data study that I showed you in the introduction, that had accuracies of less than 70%. The human performance was 70%, but this is able to do much better, to close to 80%. Right? So the data and the model make a difference. And then what we did is to add all of the unlabeled data that we had. So this is 16,800 images of different buildings. And we used a semi-supervised approach. So how a semi-supervised approach works is that you create 2 versions of your model. Okay, so I've trained it with a supervised approach. So now my model does a reasonable job at predicting things. And now I keep an online copy of the model, and I keep that online copy is called a target network, and then I keep another network that's called the teacher network, the target or student network, and then I have a teacher network. And the teacher network is not updated. The student network is updated every time. The teacher network is used to produce a label, okay, and that label is used to train the student network. So the student network is learning from the labels predicted by the teacher network, but the weights of the teacher network are slowly updated by taking an exponential moving average of the student network weights. So the student network is continuously changing. The teacher network is an average of the student network weights. And the labels produced by the teacher network are called pseudo labels, and they're used to train the student network. But by taking this exponential moving average, you have a slowly changing teacher network, you have a quickly changing student network. And then once in a while, the student network weights are replaced by the teacher network. So that allows the model to use its understanding that it's gained from the supervision to slowly expand the distribution that it has learned over, because it's able to make predictions on images it hasn't seen before. And because of the exponential moving average, the images on which it's making better predictions, or predictions for which it has more confidence, that will persist even after you take the average. Right? Those weights will persist. But if it's a sudden deviation, then that will get averaged out. So people have found that these semi-supervised methods work really well, and we adapted it to our problem, and we applied it for both of these data sets. And you can see, indeed, we observe an increase in performance, right? And it's a significant increase, because we're at 80 and we're able to, in this case, from 70 to 80, and in the case with all of the data, it's a 7% increase, so 81 to 88. And this is significant because we're able to get 88 out of 100 structures correctly assessed. So the goal was to study how the training data affects the performance. Now, if you're using a semi-supervised approach, then the unlabeled data will improve the performance. But it still depends on the amount of label data that you have. So if you have only 25%, in this case, it's around 260 images, then you can get a bigger increase with the semi-supervised learning, but still the overall performance is still lower. Right? So we were just studying how the what the increased difference is going to be when you have all of the training data. So we would expect that as you get more supervised, of course, in the limit, as you get infinite amount of training data, then the semi-supervision has no impact. But when you don't have that, then it can be useful. So does that make sense? The 25% is just from here. Okay. So here is a map from Port Aransas, close to Houston, and these are the ground truths that were assigned by researchers. These are the models predicted. These are the values predicted by our model. The difference between these two numbers. So these are integer numbers. So we can take the difference. And you can see what the different colors represent. In the last case, the difference key is also provided. And you can see that most of the circles have a difference of 0, which means they were correctly classified. And about 9% have plus or minus 1 class. So even if it's wrong, it's not off by too much. And 3% have a plus or minus 2 class. Okay, that means if it were supposed to be class 4, maybe it's classified as class 2. And, or vice versa. Any questions about that? No, this is not satellite imagery. Oh, in that one? That's not our paper. So I don't know, but which one? Yeah. So the paper, I can give you the paper author's name. It's from this data set, Kajwal et al. 2022. It's from Texas A&M, I think. Okay. I think it was, I don't want to say, it's either 50 or 30 centimeters. So this was for the case of hurricanes. For hurricanes, you get a lot of data from the roof of the structure because the main source of damage is that a tree falls on the roof gets blown away. You have a lot of timber structures in the US, which are very cost effective to build and easy to assemble. You can assemble them really fast, but you know, there's still a lot of research in how to make them hurricane proof. That's required. But because of that, you can tell a lot from the roofs, and so from the aerial imagery and the satellite imagery, you're getting good signals that can be used to understand what the impact on the whole structure is. That's not the case for all disasters. If you have flooding or if you have earthquakes, then you can't really tell too much from the roof. Another thing that we looked at is how can you do earthquake assessments using commercially available satellite data. You have a question? How was the choice of data for the semi-supervised model done? Okay. So there's this company called Vexel which collects ultra-high resolution aerial imagery, and that imagery has much higher resolution than the satellite data, and so that's why we chose that. Now, specifically, what areas did we look at? We looked at areas around regions that were affected by hurricanes in the past 7 years. We had limited ability to download images from their API because it costs them money to share that data with us. So we collected as many images as we could around Texas and Florida, which is where the hurricanes usually hit, but also near some of the other hurricanes. So if you go to the paper, we have a few more details about that. So hopefully that answers the question, but if not, let me know if you have any follow-ups. I think we're disconnected. My internet keeps dropping for some reason. Okay. I think we are back. Yeah. In this case, we're looking at earthquakes, and the problem, like I said, is that for earthquakes, you don't have as much information in just satellite imagery. Still, there's some information because there could be debris, there could be some cracks on the roof, there could be, yeah, that's fine because I'm using this map. And what we try to do is to combine these images with other types of data that are available and see if we can get a net improvement in performance. Of course, to the health of the, or to the earthquake response of the structure, the soil properties matter a lot, the shear wave velocity, VS30. Also, the intensity of the earthquake at that particular point matters a lot. And we can also, with reasonably low latency, get access to synthetic aperture radar data. So synthetic aperture radar can tell us about the deformation of the Earth and the infrastructure on top of it after a disaster, because it uses similar methods to triangulation. And it can work even through clouds, but the resolution is much lower than what you would get from optical imagery. So we combined these three sources of data and we sampled them at the locations of the buildings. And we did this for data from after the Turkey earthquake from 2023. And we proposed this model called Quake Metaformer, which combines all of this data. We call this metadata, and the image data itself using a transformer architecture. For all of this data, we're just using MLP nonlinear embedding, so a multi-layer perceptron, which is basically matrix multiplications followed by nonlinearities. And then we have feature maps, and we have a transformer, and then we do a classification. So here you can see a comparison, imagery only, imagery plus metadata. There is a significant jump in the AUC-RC, which is the area under the curve of the ROC curve. That is a metric that's also commonly used for classification. And you can see that this model does better than previous results that were proposed last year, right? This is all for the Turkey earthquake. Those were the two models that had been proposed to do classifications for the Turkey earthquake. our model does better because it's combining so many of these different data sources. Another thing we did is to look at the generalization ability with and without the metadata. The way we did that is to look at models trained on specific cities but tested on other cities. The Turkey earthquake was widespread, so we took data trained on so those are the 4 cities, right? We took the training region was Kahramanmaraş, and then we have the testing regions, which are the other 3 cities. And you can see that here, the first column, AUCRC across regions, that is with the metadata. And the second column is without the metadata. If we are just training and testing on the same region, right? So if we train and test both on Kahramanmaraş, then you can see that the difference in performance is not that high. But when we train on one region and we test on another region, then you can see there's a much bigger jump in the performance, and that's because adding this extra data allows the model to generalize better. Okay, so that's what we observed here. You can see that there's a clear difference, and that's why we get this accuracy bump in the testing data, because the test data hasn't been seen. And so the image data may have a tendency to focus a lot on things that may not matter, like debris. So debris may matter, may not matter, not sure. To decide if it matters or not, this metadata is going to be used. So that's why this model does better with the metadata. We also did some feature importance for the different metadata that we had, and then just to see which one is having the biggest effect. And the ground checking intensity has the most effect. So the PGV and the PGA, you can see, have the biggest effect, and then the spectral acceleration at 10 has also a significant effect. The SAR data, not as much. So this DPM is the damage proxy map, which is extracted using the SAR parameters, and that also has some effect. Okay. So you can use satellite data and ultra high resolution aerial imagery along with other types of data to improve your performance if you're trying to assess in the aftermath of disasters. Now I'm going to talk about another type of way to potentially improve performance, which is generating synthetic data yourself. For computer vision, one way to generate synthetic data is to use computer graphics. There's been a huge amount of advances. These days you can see CGI in movies that look really realistic. So can we use computer graphics to produce useful representations that can be looked at by AI models to learn what different features might look like? Why would we want to do this? Any thoughts on why would you want to use CGI data? Yeah, annotating existing data is a tedious process. CGI data, you could implicitly model what different parts of the model might be, and so that obviates the need for those annotations. You were saying something? Yeah, so it might be difficult in the field. Say you want to study different camera angles for your data collection. If you can do everything in a virtual world, then that can save you a lot of money, perhaps. Those are 2 good reasons. The other thing is you can have a lot of different variations. Whatever you can model, you can get examples of. The challenge, of course, it can be quite tedious to do this modeling. and it can be very hard to get it to look real. So it's not all rainbows and roses, but it's still worth investigating. We try to look at the earthquake problem. Can we generate realistic data of what a building might look like if it were to be damaged by an earthquake? And for that, we had to generate examples of buildings damaged after earthquake. So how do we do that? You need to figure out where to assign the damage. Right? If you have a model of building, you need to figure out where to put the damage. And we thought, instead of trying to come up with rules, why don't we just run a finite element analysis on a building, figure out where damage is going to occur for different earthquakes. We can run a nonlinear time history analysis, figure out the stresses and strains, and then use that to obtain a model for the location of the damage, and then we use a graphics model on top of that to render what that looks like. So that's what we did. There's a graphics mesh. So it's a parameterized building, and using the same parameters, I also create a finite element model. Make two models. One is a global model. One is a local model. The global model allows me to have a representation of the whole structure, and then I get a simplified structural response. I use that as input to a local model where I have a nonlinear concrete damage plasticity model that gives me something called damage indices, which gives me the location of where it might split. And I use that as a probability distribution to sample from, and I get ask. Okay, and I'm sampling from that probability distribution based on these curves for different damage states. And I use damage mask. So these are basically my annotations for that component, right? Because I have the cracks, I have spalling, and then I just need to render that out. I use a shader. So this is made using Substance Designer. You can use other softwares like Blender. And then I apply that to each of the components, and then I get my damaged building. So here's a close-up. On the left is that building that we saw earlier, and on the right is a CGI model of that same building. It's an approximation. I didn't have the exact dimensions, and also it's a parameterized building, so it's exactly the same. And also I didn't have the exact ground motion for that, but we kind of approximated it from whatever records were available. And you can see there's some similarity in where the damage is occurring and the shapes of the damage and the colors of the building. So with the same process, we generated many buildings and created a data set. This is called Quake City, which is available. You can feel free to download it from my website. And we can change things like the color of the building. You can change the location of the UAVs. We can change the lighting. All of these things we could change in the real world. You can also control there. And like we discussed, you get a lot of free things as it comes to annotations. You can get damage states for individual elements. That's important, especially for things like bridges. You can get the components themselves and where the column streams. So all of that information is available in the finite element model. You can get the spalling patches. You can get the cracks as well. You can barely see them here, but there are cracks. And you can also get the depth map. Question is, can we use this CGI data to improve the ability of deep learning models to learn? So we did a study. This is by my student Charles. What we're trying to do here is to see if we can learn without any real data. So it's trained only on synthetic data, and then it's tested on real data. The way to do that is something called unsupervised domain adaptation. It works in a similar way to this teacher-student network that I described for the semi-supervised. except that you're using two domains. So in the first case, we had labeled data and unlabeled data. Here as well, we have labeled data, which is the synthetic data. Then you have unlabeled data, which is the real data. And this is all my synthetic data, and then I have unlabeled real world data. We use two UDA methods, FIPA and DA former, and see how they work. And here are the results. First one is for component segmentation. This is the result of the UDA. This is the result of direct segmentation. What is direct segmentation? It's trained on synthetic data and it's applied on the real data. Okay, there's no student-teacher network that's fine-tuning based on the features in the real data. And you can see that the MIOU, which is the mean intersection over union for all the classes, it increases by a significant amount. So 29 to 41, that's more than 10 points, which is a big jump for IOUs. Again, this has not seen real labels ever. It's only seen synthetic labels. So of course, it's nowhere near as close to what you would get with supervision with real data, but it still shows that you can produce features that are good and can be improved also with the real data to do a reasonable segmentation. And then this is for the damage jump is even bigger, about 20 points, and that's an example. For this, we find that the PIPA works better. For here, we find that the former works better. We're putting together these to try to submit it soon, but that's what we have so far. Those are the IOUs for the individual classes. This is the mean IOUs, not for this image. For this image, it's going to be better. We released these data sets as part of the, in 2021 as part of the international competition for SHM. Some of you may have seen these data sets. Of course, this bridge one, the trust bridge one you saw in this class, but they're all available to download, should you be interested. We had a lot of participation, including from India. Well, we had 2 teams that finally made a submission from India, but we had more that registered. We had 50 teams, 52 teams overall, and you can see the distribution of the participation. But this data set, when we released it, it enabled a lot of research on semantic segmentation from some of the leading researchers on these topics, and we produced a special issue in the Journal of Smart Structures and Systems, and you can find all those papers as well. Okay, so far we looked at synthetic data using computer graphics, but you can also produce synthetic data using deep learning models. I'm sure all of you have produced images using ChatGPT or Stable Diffusion or something else like that. There are a lot of generative models that are able to produce images. They have some issues, but still they can be quite powerful. So what we try to do is apply some of these generative methods. This is it's an old paper now, but still the results are still interesting to look at. The idea we had is that we have a lot of examples of a lot of examples of undamaged buildings and some examples of damaged buildings. Can we use this to predict what an undamaged building would look like if it were to be damaged? There has been this problem where you're translating one image to another is called unpaired image-to-image translation when you don't have one-to-one correspondences. Many of the modern AI methods, they're good at reducing images from scratch, but if you want to modify an image, they're still not that good. So traditional deep learning approaches where you are training in a supervised way will still outperform. So there are lots of images of undamaged structures. In 2017, Zhu et al. Proposed a model called a cycle-consistent adversarial network. which allows you to do unpaired image-to-image translation. What does that mean? I have two domains, domain A, domain B. I want to learn what the features of domain A, domain B, and then I want to be able to translate images from domain A to domain B and from domain B to domain A. Examples, we have horse and zebra. You're never going to have a picture of a horse and a zebra that look exactly the same except for the stripes, because they're not the same animal, and it's basically impossible. But they have very similar features in terms of their body structure, and so you could imagine what that might look like. Here we have some examples of translation from zebra to horse and horse to zebra. You can see that there is a lot of consistency. All of the geometry and the structure of the image is retained, but what is different about the two domains is what is translated. So that's what these cycle consistent adversarial networks do. More examples, changing the style, changing the seasons, and that style as well. So how does this work? It learns to do a double translation. So it learns two networks, G and F. They're both, you can think of them as dense prediction networks, where you have an input image, output image, except the output image is also an image, not just labels. And because of that, there's you have to use a relative adversarial network. Some of you may know what that is, but for those that don't, you can think of it as a dense prediction network. So I have two of these networks, G and F. I go from my input X domain to my Y domain with G, and F goes from my Y domain to my X domain. The goal of this cycle consistent adversarial network is to make sure that a double transformation from X to Y back to X and Y to X back to Y is the same as their original images. So if I'm able to find the G and F that do this, then potentially one of the solutions of that is having these sort of transformations. Of course, if both G and F are identity, then it would still satisfy, right? But one of the solutions is where you have X to Y and Y to X. The way that you make sure that it's not just identity is that you're making sure when you do one translation X to Y, that looks like Y. And when you do Y to X, that looks like X. So those are the additional constraints that you impose. So can we do this for damaged to undamaged and back? We used the images that I collected in Mexico City, and we divided them into two parts, damaged and undamaged. You can see the details of those. And then we tried to apply this Zhu et al. From 2017, but it didn't work so well. And we thought maybe that's because our data set is not that big, because many times sometimes it would work, but many times the translation would be just this identity translation. So it's not doing anything. So we thought, how can we tell the image tell the model what we want it to be looking at? This is our proposed network. It's called GIAN, because we use something called an eigen class activation mapping. If you do a classification problem, then you can run something called a class activation mapping and figure out which parts of the input were responsible for making that classification. It's like a heat map that tells you what part of the input the network is using in order to make that classification. Because we have a damaged, undamaged data set already, I can easily do a classification. And of course, the classification models can do that sort of task very easily. Okay? And once they've done it, they're really good at identifying the features that are relevant to make that decision. So we thought, can we help this cycle consistency network do the kinds of translations we want by giving it also this heat map that is produced by the classification, because the classification network already does the hard work and figures out what features are important. We just give that to this network. So we get the eigencam features, and we concatenate it with the inputs, and then we use that to then do the translation, and this we published in Advanced Engineering Informatics, and the results are better than the cycle time. Here is one example. We have an original image, we have translated image, double translated image. You can see that the network figures out that above the windows you typically have reinforced concrete beams, and then above that you have some masonry that's being exposed. You can see the types of damage there. Here are more examples. All the images on the left, those are the original images. The images on the right, which are this, and this, those are all translated images. The network is learning patterns of where damage tends to occur, what that damage tends to look like in relation to the components. Sometimes it also does paint color changes or brightness changes. Right here, this building, in our data set, we had images of it after it was fixed, and they painted it a different color. So you can see that translation. It's kind of learned that. But you can also see that it's learned that the damage might occur at the stress concentrations where you have smaller area, and those are the results. Another thing we did is to look at, can we get a little more control in the damage that we are producing, so that we can have more variation. If you go into the latent space, which is this bottleneck part of the network, if you make changes there, then that will change what the image looks like. So we just need to find 2 points in the latent space, one which corresponds to less damage, one which corresponds to more damage. Then if we interpolate between these 2 points, we get images also with less damage and more damage. So how do we find these 2 points? Well, with this unpaired image-to-image translations, you're sort of limited because you don't have any way to control the latent space. But one thing you can do is to just use your network. So if we apply our network twice, first time the structure gets damaged, second time it gets more damaged, then we get 2 points, and then we can use that and do interpolation there. And that's what we did here. You can see as we interpolate, the amount of damage does indeed increase. And here are more examples. You can see the crack emanating from the corner, and then it's growing and getting worse. Now, what can you do with this synthetic data? Well, the first thing you can do is just to measure to see how good it is. And the way to do that is to measure the distance between the distributions of your synthetic data and your real data. If those distributions are close to each other, then your synthetic data looks like your real data. And if they're far, then it looks different. And there are different ways to measure these distances. Essentially, you're getting feature vectors, and you're using the distribution feature vectors. We have the kernel inception distance and the Fréchet inception distance. You can see that IGAN has a lower distance than these other methods. And we also used the synthetic data for data augmentation. So we take the synthetic data produced, and just like how we did transformations like cropping, zooming, rotation, you can also do translation using these networks as a way to augment your data set. And you know if it's damaged or not because of the network that you're using, provided you know how you're starting. So we have the undamaged images, the translated images, and then we have a real damaged data set. And then what we did is to augment this with the damaged data set and the real data, and we vary the amount of real data that we're adding to see in what scenarios the augmented data will be useful, and also to compare the different networks that we had. So we use the area under the ROC curve, similar to what we did in the earthquake example, satellite earthquake example, and you can see that IGAN performs better. But as the number of real images increases, the performance does increase, but the difference between real images only and GIAN also reduces. So here the difference is just 1, but here the difference is 0.2. Small numbers, but still you can see that trend. Okay, any questions about that? Okay, so far we looked at 3 types of synthetic, or 3 types of methods to improve performance with limited data. One is semi-supervised, and then we looked at CGI, and then we looked at data-driven generative AI models. Okay, now we'll look at some other topics. The first one that I'll talk about is anomaly detection. So we define this problem called scene anomaly detection, where you have a bunch of images. You have a bunch of images of a scene taken at one time step, and then you have another bunch of images of that same scene taken at a later point in time, and you want to see if there's anything that is different about that scene. Now, what we are not assuming is that we have the same camera views. There's been a lot of work on change detection and anomaly detection, but they typically rely on having the same view of the scene. But in the case of civil infrastructure, because they're so big and because the precision of our data acquisition instruments, like robots or manual capture, they're not so high in terms of their location, we're often left with a scenario where it's very difficult to perfectly align the images. So here we're trying to see if we can find changes even without this alignment. And we're assuming that we have multiple images of this. To test this, we built a toy dataset called Toy City. And it's basically toy buildings and road and some signs and a background. And what we did is to have some baseline combinations of the city and have small variation. For example, in this first city, we have the sign being removed, and you can tell by looking at these two that it's the same building if you look carefully. But for a computer vision approach, it's much harder to tell because they're not perfectly aligned, these two things. Right? Here and here also, if you look, you can tell that they're the same building, but this top piece is missing, and then here we have the road, and then there's the parking sign. So we had different anomalies for these different baselines, and we used that to test a method that we developed. So this is called Omni-AD, or Omni Anomaly Detection, and we do two things. One, we improve upon existing anomaly detection methods, but second, we adapt it for this problem of scene anomaly detection. How do we do that? We use novel view synthesis approaches. So novel view synthesis allows you to generate new views of a scene. And there are different ways to do that. One is called a neural radiance field. Another is called Gaussian splatting. I just want to see if I have slides for that, or yeah. So one way to do a novel view synthesis is through something called a nerf. You have a bunch of input images. You can do the initial calibration and generate the sparse point cloud like we did in reality capture. And you can localize each of those images and get a point cloud. But then our goal is to generate a new view of the scene that is not necessarily in the original set of images that you use. So say I take a picture from here, and then I take a picture from here, but then I want to generate a picture from here or somewhere else. So I can specify the location of the camera that I want to generate the view from, and I can generate a novel view. That's what these methods do. There's a lot of research in how to improve them. They can be quite memory hungry. These days they're getting more efficient, but essentially it learns the mapping from the camera position to the image. Okay, so in the case of nerfs, it's or to each pixel position image, and in the case of nerfs, they're using a multi-layer perceptron. In the case of Gaussian splatting, they're making assumptions about, well, they're using traditional rendering techniques that you would do in game engine, where you have, for each point, you have some Gaussian splat, and you're using a blending of those splats to render the image. I won't get into those details, but essentially this allows us to generate new views which are sort of realistic. Okay, more realistic than taking a screenshot of a textured photogrammetry mesh. So so let's look at the steps of our pipeline. We have our scene, and we have some baseline views, and then we have some anomalous views. In the anomalous views, they may not necessarily be the same as the baseline views, and the scene may have changed. Okay, so that's what this means. We do SFM in the baseline, so that registers all the cameras and know where the cameras are. SFM is structure for motion. We looked at that, and once we do that, we test two different novel view selection strategies. The first one is called interpolated baseline views. So all we're doing is we have all our baseline cameras. We're interpolating between those. So we're just getting some more views in between those. And then, well, this is what that would look like. If we have 3 camera poses, then we have some views in between. And then we do another thing, another way of generating novel views, which is called anomaly aligned baseline views. So what we do is we take each of the new images that we have, and we try to register those images to the old scene, to the baseline scene, and we figure out the camera pose of the new image in the old scene. And once we do that, that may not be perfect because the scenes have changed, and so there may be some, and then also the view may be quite different. But we do that, and then we get that point. So say that's an anomaly pose, then we try to generate a novel view of the baseline scene from that same pose. So that's the novel view of the baseline scene from the same pose, and you can see that there's some difference right here. There's some ish parts that are produced, but between these two images, once they're aligned, it's going to be easier for you to tell the difference, right? What's the difference between these two images? Which one? Left side top corner? That one? Well, yeah, I mean, so there's a, so that's because the novel view synthesis is not perfect, right? You can't tell for sure that that building has changed. It's just that the view is not perfect. So there are issues with the novel view synthesis, but can you tell the difference between the anomalous scene and the baseline scene? Yeah, right. So it's very obvious now because you have this parking sign here and you don't have it there. So for the network also, if it has this example, it's going to be easier for it to tell the difference. That's the hypothesis. You use an incremental SFM where you add an image, so you can add more images and register to this. Yeah, so you match the features of the new image with the original scene, compute the new camera matrices. I mean, just the same SFM process, right? So what's the SFM process? You have images, you do the feature matching, and then you triangulate and obtain the camera poses. These two images, well, this is after all of that's done, but you're assuming that you have some features to which you can match that original scene. And if you don't, then the interpolated view will probably work better. Okay. So that's the idea. And then we have a novel view synthesis once you choose the strategy, which we're using a nerf for that. And then from the anomalous scene, we have the anomaly view, which is the picture that was taken, so no changes to that. And we're using these sets of images to train OmniAD. Now, there's no ground truth changes used for the training. It's done in a fully unsupervised way using an approach called reverse distillation. It produces a heat map and then you need to threshold. So for the threshold, you need to provide a value, which you can do using a few examples. So that is the only supervision that there is. But the heat map, all of that is done in an unsupervised way. So what is the OmniAD architecture? It's a modification of the reverse distillation architecture, which was proposed 2023. The modification we make is to add these attention maps. So we have a teacher encoder and a student decoder, and then we have a bottleneck. It's similar in the OmniAD, in the reverse distillation architecture, except that we change the teacher encoder from a ResNet to a ResNext architecture, and then we have these attention modules for the student decoder. The idea is that, so with the reverse distillation, what is happening is that you take this image, you pass it through the teacher encoder, and you get this bottleneck. And then you're using a student decoder to interpret that bottleneck to find out where the perturbations are. But the student decoder is getting its weights, it's distilling its weights from the teacher encoder. I won't go into the details of how that happens, but the idea is that if you have a new image which is different from your baseline scene, then it's going to cause some perturbations in the teacher encoder, in the teacher encoder. And if the student decoder is attentive to those changes, then it can point to where those changes are. So if the student decoder is more attentive or more sensitive to changes, then it's going to be able to do a better job. So we want large perturbations to occur when an anomalous image is given, and so the student encoder helps with this. So this is the details of the attentive student modules that we demonstrated, that I showed you in the previous slide. But we did some experiments to see the effect, and we found that it, including these student attention modules, increases the effective receptive field. So the receptive field is the part of the image or part of the input that a particular layer is sensitive to. As you progress, then you can see that the size of the receptive field is going to increase. And also, different things can affect the receptive field. If you have different nonlinearities, that also can influence it. So the encoder, in our case, has a smaller effective receptive field, but then when you add the attentive student module, you can see that the receptive field increases a little bit, and we find that this helps be more perceptive to changes across the whole image. And then we compare the different novel view synthesis methods. So we have V1, which is only baseline views. So every time you are going to do an anomaly detection for a scene, you need to train your network on that scene. And then for inference, it happens fast. You just have to register that image, figure out the camera pose, and then you can run your inference. So we have V1 only baseline views. V2 is baseline views with the anomaly aligned baseline views, and then we have baseline views with interpolated baseline views, and then we have baseline views with all of the views. So all of this is the training data that is used to train OmniAD. And then when it sees a new image, it already knows what that scene looks like from different views. And if there's a change, then it should spike, and then you can do a semantic segmentation by applying a threshold. Okay. So here we can see a comparison. So again, this is unsupervised because there's no direct supervision. You're just learning features of your original scene. When you get a new image, you're seeing something change. The network is seeing if it thinks that that new image is different, and it produces a heat map, and then you threshold. So you can see that on the top row, I have different models that have been proposed for anomaly detection. Now, all of these models have been proposed for single view constant camera anomaly detection. There's not been work on multi-view anomaly detection. There's been some view on multi-view change detection, which can be supervised. But in an unsupervised anomaly detection approach, there's not been work. So you can see our model does better than all of the other models. RDR is also something that we did. So RD is reverse distillation. RDR is reverse distillation with ResNext, and ours is reverse distillation with ResNext and the student attention modules. And you can see that for all these cases, V4 performs the best, or not for all of them, except I think all except Toy City 2. Actually, that's not true. So V4 performs the best for Toy City 1, and V2 performs the best for Toy City 2 to 4. So V2 is the anomaly aligned baseline views. So that works better than just interpolating, and that's because if you're just interpolating, that doesn't necessarily give you the views that the anomaly is in, right? But in case one, the combination does a better job. And you can see that the difference between reverse distillation and OmniAD is quite significant. It's close to a 40% increase. We're just looking at these F1 scores. These are pixel-wise F1 scores, so it's like as challenging as the IOU. But none of the other methods report IOU, so we're reporting what they report. Yes. You can. But then also you would use reverse distillation. That's the state of the art. That was the state of the art. But the thing is, they're not perfectly aligned. Even with the novel resynthesis, they're not perfectly aligned. There are artifacts that you get from the nerve. So you have to make your method robust to all of that. If you have a perfect alignment, yeah, but the thing is, even if you use SFM, the alignment is not perfect. because you have a new scene, there may be some changes, and you have to use an owl view synthesis to get the new view. Say even if your camera pose is perfectly aligned, that new view may have some artifacts, and so you have to, if you have a supervised approach, you can do it, right? If you have lots of examples, but then in that case you can probably just do a supervised learning directly. So if you don't know what change you're looking for and you're trying to find a change, then you have to use an anomaly detection approach, and that's what we're doing here. Yes. 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 But the reverse distillation works better than a simple autoencode. But you could do that. So these are you know the top performing anomaly detection methods. Okay. And you know some of them are what you described, but they just have some fancy names. So here are some results. We have some anomalous images. We have the ground truth, and then we have Omni AD results. Then we have reverse distillation results. You can see reverse distillation gets it wrong here, and then misses it here completely. But Omni AD is able to get those examples. You can look at the heat maps also, right? So the supervised step is determining the threshold, but you can see that it's able to localize that region, right? So